Next topic will be Markov processes, which, as we'll see quickly, is very much an equivalent to the state space definition or the state vector definition in the context of linear systems. So, Markov processes are defined by the following property, which is called the Markov property. Given a random process, x of t, its probability density function at time t, p of xt, given the set of its values, x tau, up to and including some point t1 in the past, is p of xt given only the value at this most recent point t1. In other words, the past up to any t1 is fully characterized by the value of the process at t1. As you can see, that's somewhat equivalent to the definition of the state in dynamic systems. The difference is that here we have full characterization that is a probabilistic characterization as opposed to a full information or full description of the behavior of the system in a deterministic situation. Now, we can make an equivalent statement to this as follows. The future is independent of the past if the present is known. Now, the winner process is Markov, and this follows from the fact that it is the integral of white noise. Now, with an arbitrary initial value, w at time t is w at time t1, the initial point, plus integral from t1 to t, n tau d tau, where n of tau, for tau in the interval t1 to t, is independent of its previous values. Therefore, what we can see is, in a more general dynamic context, is as follows. The state x of t of a possibly time-varying dynamic system driven by white noise, n of t, namely, the dynamic equation is x dot of t is some function of t, that's the time-varying part, of x of t, the state, and n of t, that's the input, the noise. This is a Markov process. In general, both x of t and n of t will be vector-valued random processes, but it's very important that if the noise is white, the state equation yields a Markov process, and this connects even more the concept of Markov process and state space. Now, let's go a little bit into the frequency domain, and we'll look at Markov processes which have a certain autocorrelation function, are stationary, and have a spectrum, and we'll consider those with a rational spectra as follows. If we are given a linear time-invariant dynamic system excited by a stationary white noise n of t with mean 0, x dot of t is axt plus bnt. So a and b are time invariant, so that's a linear dynamic system, time invariant. The state, x, in steady state, in other words, we do require now the system to be stable, will be a stationary Markov process with spectrum or power spectral density. S of omega, that's the Fourier transform of the autocorrelation of x coming out from the system, is h of j omega q h of j omega conjugate. H is the transfer function of this dynamic system. Q is the power spectral density of the input noise. This transfer function, h of j omega, is related to the state space description as follows. H of j omega is j omega I, that's the identity matrix I, minus A inverse times B. So this is the transfer function matrix from the input vector to the state vector of our system. And the autocorrelation of the input, again in general a matrix, is Rn. Sometimes we use notation Rnn, sometimes just Rn. Now there's no other variable, so it's a single subscript. The expected value of n at t1 times n at t2 transpose. This is an outer product is a matrix, with n being a column vector, is a Q delta T1 minus T2. Now Q again is really the power spectral density, a matrix of this vector valued random process, even though sometimes it is called the covariance, but this is not a correct designation because I indicated that delta has a dimension, and typically the variance of a quantity should have the dimension of the square of the quantity, and the delta changes because it introduces the factor of 1 over time there. Now, if we go back to this equation of the transfer function and the product of the transfer function with the constant matrix Q and with its complex conjugate is the spectral density of the state. What we have is, because H is a rational function, remember, linear time invariant system will always have a rational function. Looking at this is just the inverse of a matrix that's a polynomial. So it would be a ratio of polynomial over polynomial. Therefore, we have a rational spectrum for the state X of a linear time invariant dynamic system driven by white noise. Now, it's even more interesting that we have a converse result. Every Markov process with a rational spectrum can be represented as a linear time invariant system excited by white noise. So what we have is there is a system which, if excited by white noise, will yield a state or an output, depending on what we are interested in, with a spectrum as specified by a certain equation we have seen, and this is how it connects to the transfer function. So, and there will be a system for every rational power spectrum output. Okay, the use of state estimation is primarily for Markov processes. It turns out that the models that we are going to rely on will be all Markov processes. And if they are not Markov, we have to transform them so they become Markov, because the tools are pretty much exclusively developed for Markov processes. They can be linear or they can be nonlinear systems driven by white noise. These systems can be time invariant or time varying. The noise can be stationary or non-stationary. We have a lot of latitude here. If we have a time invariant system driven by a stationary noise that is not white but has a rational spectrum, that we have to transform it into something via pre-whitening. And this something will be a Markov subsystem whose output is Markov. Namely, the output of a subsystem driven by white noise. We'll see such an example in a short while. Now, the transfer function of this subsystem is obtained by spectral factorization. So everything will be rewritten such that it is a dynamic system somewhere driven by white noise and nothing else. So the not white noise with a rational spectrum is pre-whitened, so it is really the output. The colored noise is the output of a white noise driven system. But the way to do it is what we call spectral factorization, namely the decomposition of the output spectrum in the form of HQ, H transpose. And there's a wealth of material in the literature, much more detailed than what we are going to cover, but we'll see some interesting example. How do we do pre-whitening? Pre-whitening, we'll see it in a couple of figures in a moment. Here's the first one. Here's a system, S, driven by a noise which is not white. So X is not Markov. What we are going to do now, we augment this system such that N is the output of a white noise-driven subsystem S sub 0. And now we have N is Markov, and N and X together are Markov, because these are really the output of a larger system driven by white noise. So this is the way to carry out the augmentation. So what we are going to do is, to recapitulate, n of t will be the output of the subsystem S0, the pre-whitening system, or shaping filter. The reason it's called shaping filter is because the input will be white, that it has a flat, constant spectrum, and the output has a particular shape in its spectrum. So that's why it is called shaping filter. So would X0 being the state of this pre-whitening subsystem, the augmented state of the composite system, X and X0 together denoted as Y, is then a Markov process. Here's an example. Consider the random process X with this spectrum, a constant over a squared plus omega squared. How do we factorize it? We can decompose clearly the denominator as the product of a plus j omega with a minus j omega. Remember that the decomposition will have to be done in a manner that one of these will be H, one of them will be H complex conjugate. The question is, which should be H, which should be H star? You can easily identify as a causal transfer function the first, that's why we wrote it in the first place here, 1 over a plus j omega. So this will be H, and this will be H complex conjugate, and then H is the transfer function of a system x dot equal minus ax plus n, driven by the white noise n. So this shows how you can decompose or factorize the power spectral density of some random process such that you can rewrite it as the state of a system driven by white noise. Therefore, it falls in the category of a Markov process. Now, a lot of the work we are interested in will be done in discrete time, where instead of random processes, we have random sequences, and we have Markov sequences and Markov chains, and we are going to cover these topics next. A random sequence, which is nothing but a discrete time stochastic process, is a time index sequence of variables x at time j. J goes from 1 to k, and we denote it as a cap x superscript k. So that's like a cumulative index, the upper limit of our index, and the lower limit is 1, and we are not going to indicate it now. Similarly to the continuous time definition of the Markov processes, if we have a random sequence, we say it is Markov if the probability density function of x at time k, or number k in our indexing system, given the past x super j for j less than k, is the PDF of xk given x at j only, which means out of this whole bunch of conditioning variables, only the last one matters. It summarizes probabilistically the system. Now, if we have a real valued scalar, zero mean sequence v of j, this is a discrete time white noise, or a white sequence, if the autocorrelation E of vk times vj is some q of k times delta kj, and now this is the Kronecker delta function, which is either 1 if k equal j or 0 otherwise. So now q of k is indeed the variance of this process. When k equal to j, E of v squared k is qk times 1, so it's q of k. And if q different than j, it is 0, which means it's at any point in time, it is uncorrelated from any other point in time. These are discrete points, and this will be the variance. So this qk in general can be time varying, if it is a constant, namely time invariant, then the variance is time invariant. We already made it zero mean, so that's obvious. The first moment is time invariant, the second moment is time invariant, so what we have is a stationary white sequence, if qk is a constant q. Again, this is wide sense stationarity. Now, similarly to the continuous time case, if you have a white sequence deriving a dynamic system, and we see the equation in a moment, in discrete time, the result is a Markov sequence. Take the state xk of a dynamic system excited by white noise. Xk plus 1 is f of k, time varying, and xk and vk, that's the input. This is a discrete time Markov process, or a Markov sequence, if vk is white. So, take a state equation, its state becomes Markov if it is driven by white noise. Now we go further and have a linear dynamic system. This could be nonlinear and time varying. Now we just specialize to a linear case where xk plus 1 is a cap f of k, that's a transition matrix from time k to k plus 1, plus times xk plus vk. Now, this will be a Gauss-Markov sequence if the input v of k is not only white but also Gaussian. And the reason for this is that all those linear transformations preserve the Gaussianness, and the fact that this is a dynamic system causes v white at the input to yield an x Markov at the output. So the state is Markov and it is also Gaussian, so that's why it is a Gauss-Markov sequence. A special case of this for a scalar x would be xk plus 1 equal xk plus vk, in which case x becomes the integral or the sum of the white noise sequence terms, and this is a discrete time Wiener process. Remember, in continuous time we showed that the Wiener process is the integral of continuous time white noise. Similarly, in discrete time, a discrete time Wiener process or Wiener sequence is the sum of white noises, which is exactly what this dynamic, very simple dynamic equation yields us. Markov chains are a further specialization of a Markov sequence to the situation where the state space is discrete and possibly even finite. We're dealing with a finite state space. So x at k is an element of the set of x sub I where I goes from 1 to n. So there are n possible values for the state. Its characterization is given for such a random sequence, a Markov chain. All you have to know is the so-called transition or jump probabilities. P of xk is xj, namely at time k the value is number j, if at time k minus 1 the value was I, xk minus 1 is xi, is a pi ij, the jump or transition probability from state I to state j. So what we need is A, it's Markov, B, we have the transition probabilities from one stage to the next, and we obviously need the initial probability vector. Another important result that we will use in this course is the law of large numbers and the central limit theorem, which is a refinement of it. What the law of large numbers, LLN, states, loosely speaking, is the following. The sum of a large number of random variables tends, under some fairly mild conditions, to its expected value. Add up a lot of random variables, you get their average. Effectively, what happens is the randomness pretty much cancels out among them. Given a stationary sequence of random variables xi, which means each of them has the same mean x bar, we said it's stationary, and covariances. E of xi minus xi bar, which is really x bar, xj minus xj bar is sigma square rho I minus j. This is invariant here. This is invariant. Obviously here we could replace the x bar j and x bar I by an x bar. Where we have these correlation coefficients, rho I minus j tend to 0 as I minus j in magnitude goes to infinity. So what we have is the autocorrelation of this process is some constant, and as the 2 points in time, discrete time, get farther apart from each other, you have them become uncorrelated. So these are asymptotically uncorrelated. So that's a sequence of random variables, which is a random sequence that is asymptotically uncorrelated. Now there's a requirement that these correlation coefficients tend to 0 sufficiently fast, an exponential decay is good. Then the sample average, we define yn as 1 over n sum of xi I1 to n. So this is the sample average of the first n values, will converge as n tends to infinity in the mean square sense to its expected value, yn bar, which is 1 over n sum of x bar, but these are the same, all the same now, I1 to n, that's nx bar over n, that's x bar. In other words, the mean square convergence says that the variance of yn, the mean square value of yn about its mean, tends to 0 as n increases. This is convergence in mean square sense. Now the central limit theorem tells us something even stronger, that if you have a sequence xi consisting of independent random variables under again some reasonably mild conditions, the PDF of the sum, we have a slightly different normalization. Before we had normalization 1 over n, now it's 1 over root n. The reason we need 1 over root n here is so the variance of this does not go to 0 but goes to a constant. Zn is 1 over root n sum of xi I1 to n will tend to a Gaussian PDF. So this sum will become Gaussian as n goes to infinity. Now if we specialize and have these random variables independent and identically distributed, IID, 0 mean and with variance sigma square, then Zn tends to become normal, asymptotically will become normal with 0 mean and variance sigma square. We defined yn as a scaled version of Zn. The central limit theorem will hold also for yn, which is in the law of large numbers. So if the random variables xi are independent, identically distributed, IID, then for large n, yn is Gaussian, would mean yn bar and variance sigma square yn, where yn bar is equal to x bar, because that was 1 over n sum of xi, I going from 1 to n, and the variance of yn, sigma square sub yn, would not, we are not going to prove it now, but we'll come back to this expression later, is 1 over n square sum of sigma square, all the same, there are n such summands, divided by n square is sigma square over n. So the variance indeed goes to 0, but in addition to that, it is also in view of the second result, the central limit theorem, this also will be Gaussian when it is close to the limit. So this is the mean and the variance of yn, our 1 over n sum of xi. A note on the central limit theorem. It has a very important role in characterizing many real-world sources of uncertainty. It is used as a justification, sometimes an excuse, but it's pretty good, to make the omnipresent Gaussian assumption. For example, thermal noise in electronic devices as the sum of many small contributions is indeed very close to being Gaussian. So what we have is a lot of small contributions put together give you Gaussian distributions. We are pretty much done now with probability theory. The next topic for the background that we will need is statistics. So we'll now carry out a brief review of statistics, which will focus on hypothesis testing. We are going to consider the following hypothesis testing problem between two simple hypotheses. Each hypothesis is defined by a point, a certain value of a parameter. We have the so-called null hypothesis, h sub 0, is that the parameter takes the value theta equal to theta 0. The alternate hypothesis, h1, that the parameter theta takes the value theta 1. And these are the two possible values. And we'd like to make a decision based on some observation as to which of those hypotheses should be accepted. And clearly, in the presence of uncertain observations, we can never make a decision with perfect reliability. So we'll define what is called a type 1 error. PE1 is the probability of declaring H1 or accepting H1 when H0 is true, and the type 2 error probability will be accepting H0 when H1 is true. In signal detection, if H0 stands for signal equal to 0, signal is absent, no signal, and H1 stands for signal present, the type 1 error is a false alarm because I say, yeah, there is a signal when there is no signal. And the type 2 error is a miss because I say there is no signal when there is a signal. And the difference to unity of the type 2 error is the so-called detection probability, which in statistics is called the power of the test. So the power of the test, pi, is the probability of accepting H1 when H1 is true, which is 1 minus the probability of the type 2 error, and it measures the test's capability to discern H1 when it is true. That's what we call in electrical engineering the detection probability. Now, the decision as to which hypothesis to accept will be made based on a set of observations Z, and we will need a probabilistic characterization, so probability density function of Z conditioned on H0 and the probability density function of Z conditioned on H1. Using this, we can make a systematic and intelligent decision which hypothesis to accept, and we can make even an optimal decision. The optimal decision follows the so-called Neyman-Pearson lemma. And the way it is formulated is as follows. We want to minimize the probability of type 2 error or maximize the power of the test or maximize the detection probability subject to a given maximum allowable probability of type 1 error or false alarm. And this is, the test is as follows. It is based on the so-called likelihood ratio. And the likelihood ratio of hypothesis H1 versus hypothesis H0, lambda of H1, H0, is the PDF of the observations given H1 divided by the PDF of those observations given H0. If we put in the observed values and come up with a number, which will exceed a threshold that we'll find out how to obtain in a short while. If it is above that threshold, you accept H1. Why? Because this is more likely to fit the probabilistic description of the observations under H1. If it's below the threshold, you will accept H0. The denominator wins. Now, how do you obtain the threshold? We'll obtain the threshold such that the probability that this likelihood ratio exceeds the threshold under the null hypothesis is the allowed type 1 or false alarm, type 1 error or false alarm probability. So this is the procedure to obtain the threshold. The probability density function of the observations Pz given Hj, and that's j equals 0, 1 in this case, is called the likelihood function of the hypothesis Hj. This tells us how well the observations fit that model, that Hj is the true hypothesis, and this gives us the likelihood of the corresponding hypothesis. Let's take an example. We'll look at the test between our hypothesis, simple hypothesis, H0 saying that theta 0 is 0, and H1 says theta 1 is greater than 0 based on a single observation. Now, this is really a simple hypothesis. This is not a simple hypothesis anymore. It's really a composite hypothesis because it's a bunch of points and we don't know the value of the point, or points, all we know they are positive. So what we are trying to do is, based on an observation z, which is Gaussian, with mean theta and variance sigma square, we want to see, is the mean of these observations 0? Really, this would be just one observation, later we'll have more, or it's positive. What is the likelihood ratio in this case? The likelihood ratio, lambda h1 h0, is the PDF of this single z given h1 over the PDF of this z given h0, which is this density in the numerator. The normalizing constants cancel out. They are already not shown. It's z minus theta 1 minus z squared, because it's z minus 0 square, over 2 sigma square. So this is my likelihood ratio. As you can see, z appears in a single location here. So what we have to do when we compare this exponential with a constant, we can conveniently take the log of that exponential, incorporate all the various constants into the threshold, and then figure out the threshold. So, because theta 1 is greater than 0, comparing our likelihood ratio to a threshold is equivalent to z being above some value little lambda 0, that's the new threshold to be determined. If it is above it, we accept h1. If it is below, we accept h0. And now we want to find out the threshold based on the maximum allowable force alarm. Okay, the PDF of the observations under h0, remember, force alarm is the probability of accepting h1, of falsely declaring a detection when there is nothing there. Falsely saying that we have a theta that's positive when it's really 0. So the PDF of z given h0 is Gaussian, argument z, mean 0, variance sigma squared. This is my likelihood function under the null hypothesis. And you can see here how the decision would be. This is the PDF under the null hypothesis. This is the PDF under the alternate H1 hypothesis. Somewhere there will be a threshold lambda 0. If my value of the observation z is above lambda 0, I will say I accept h1. If it's below, I will accept h0. And we'll come back to what these shaded areas are in a moment. The threshold for the false alarm probability, PFA, the maximum allowed probability PFA is alpha, follows from setting PFA, which is type 1 error probability PE1, which is the probability that z exceeds the threshold lambda 0 to be determined under the null hypothesis, namely when the mean is 0, is integral from lambda 0 to infinity of the Gaussian density with argument z, mean 0, variance sigma square times dz, and this should be alpha. Now, this is really the tail probability of the Gaussian above lambda 0. This is this area. So the area here, remember, the area under PDF is 1. The tail obviously will have a probability less than 1, and we typically are looking for alpha of 5% or 1% or something like this, typically small. So this area will be the false alarm probability. So that's the tail mass or tail probability. Under H0, there is only a small probability alpha that Z falls in that shaded tail region of the likelihood function of H0. That's the one with 0 mean. If it does fall there, then it is deemed unlikely that H0 is 2. It's too far from 0, and it is rejected. I reject H0. In this case, in language used by statisticians, the level of significance of H0 is low, alpha or less. So for Z equals Z1 exceeding lambda 0, we have such an observation in an even smaller tail mass. The farther out past lambda 0 it is, the smaller the probability. Now, the type 2 error probability, that will be the miss probability, P2, is the probability that Z is below lambda 0 under H1, which is the integral from minus infinity to lambda 0 of the Gaussian density, argument Z, mean theta 1, variance sigma square dz. This is the striped area in the figure we just shown. The striped area is the integral of the likelihood of H1 from minus infinity all the way from the left up to lambda 0. This is the miss probability because in this case we believe, yeah, it's likely that it came from H0, we accept H0, and mistakenly we reject H1. The power of the test, the probability of detection, PD, that's the electrical engineering notation, that's the statistician's notation, pi, is P of Z greater than lambda 0 given H1. That's the integral of lambda 0 from lambda 0 to infinity of the Gaussian density, argument Z, mean theta 1, variance sigma squared dz, which is 1 minus the type 2 error probability. Now the catch is this depends on theta 1. The farther theta 1 from 0, the bigger the power of the test. But what the name and Pearson lemma tells us, you've got the best test. You don't know how good it is, but you got the best. Because the best is understood, the highest possible probability of detection, the lowest possible type 2 error under a maximum allowable type 1 error or false alarm probability. Let's take an example. As I said, typically we allow 1 or 5%, in this case we take 5% allowable false alarm probability. We obtain the threshold, and this is from tables we'll see in a short while, based on the one-sided tail, the upper tail or right tail of the Gaussian PDF, and this is lambda 0 is 1.64 sigma. To the right of that we have 5% probability mass. Now, table below shows the power of this test as a function of the separation of the two means. And for convenience, this is in units of sigma, the common standard deviation. So it's either theta 0 is 0, theta 1 over sigma, with a 5% false alarm probability. If the value of theta 1 is twice the value of sigma, we have a 64% power or detection probability. And if it is 4 sigma, it is 99%. So as you can see, it grows very rapidly, but it is not high unless theta 1 is at least 3 or 4 sigma.